And number 13, we want to solve this, and what I'm going to do here, I could take log base 7 of each side, and that's fine, and if you want to do it that way, that is perfectly acceptable. I'm going to go right to taking the natural log of each side. That's kind of the mode that we're in and kind of what we're used to, so I'm just going to take the natural log of each side. When I do that, it allows me to bring this exponent, the x minus 5, out front as multiplication times that natural log of 7. And now I can divide. I'm going to divide by this natural log of 7 on each side. So I get x minus 5 equals the natural log of 100 divided by the natural log of 7. And notice I hold off on plugging this into my calculator until I get to the very end because I don't want any round off error. Not that I'll have any in this particular problem, but I want to avoid that as much as possible. So now this is just a job for my calculator. I'm going to be plugging in the x natural log of 100 divided by the natural log of 7 and then adding 5 to that. Okay, so I'm going to plug that in. And when I do that, I find out that x equals a 7.366, and we'll do 4 decimal places 6. Okay, that's it. If I look at the next one is a little bit more complicated. I'm going to give myself a good amount of space here. Let me rewrite this real quickly to give myself a little space in front of each of these. I'm still going to go right to taking the natural log of each side, so I'm going to take the natural log of each side. When I do that, I can bring the exponent out front, so it becomes an x plus 2 times that natural log of 5. Over here, I can bring the 2x out front. So now what I want to do is I'm going to treat these natural logarithms as just plain old numbers, because that's essentially what they are. Granted, I don't know what the numbers are yet, so they kind of act like variables in that same way. So when I distribute that natural log of 5, I'm going to just have x natural log of 5 plus 2 natural log of 5. I'll just write the things side by side. I can't multiply them until I'm ready to plug this into my calculator. Equals the 2x natural log of 8. And now I just have to gather my x values. I want all my x values on the same side, so I'm going to subtract the x natural log of 5 from each side. So I end up with a 2 natural log of 5 equals a 2x natural log of 8 minus x natural log of 5. And now that I have my x values gathered together, I can isolate the x by factoring it out. So I factor out the x, which leaves me with a 2 natural log of 8 minus the natural log of 5. And now what I have is x times a number. Granted, it's a very ugly number. That whole thing in parentheses is just a number. So I have x times that number. I'm going to divide by that number on each side. So I divide by that 2 natural log of 8 minus the natural log of 5. Whatever I do to one side, I have to do the other side. And then it just becomes a game of plugging into my calculator correctly. All right. If I'm plugging into my calculator all in one shot, let me pull my calculator up so you can see how that works. If I want to do this all in one shot, I have to put the parentheses around the entire numerator. So parentheses 2 natural log of 5. And again, that 5 needs to be contained in parentheses. And then I need another parenthesis to contain my entire numerator. Okay. Then I want to divide it. And again, the entire denominator has to be parentheses. So parentheses 2 natural log of 8. The 8 needs to be contained, so I know it's in that logarithm, minus the natural log of 5. That 5 needs to be contained, so I know it's in the logarithm. And then I need to close the parentheses so that I have parentheses around my entire denominator, and then I hit enter. Okay? And that gives me that x equals 1.2626 if I'm rounding to 4 decimal places again. When I plug this into the calculator, typically here's what I'm going to plug in. If I bring this up here, right here, the 2 that's out front, I could bring up here as an exponent. So me personally, I would use my properties of logarithms, so it becomes the natural log of 25. And then in the denominator, this 2 can be brought up as an exponent as well. So it becomes the natural log of 64. And then these 2 logarithms can be written as one logarithm, the 2 things being divided. So a quick couple operations using my properties of logarithms, I'm now going to be punching in the natural log of 25 divided by the natural log of 64 over 5, which I'm going to show you real quickly. That'll give you the same answer, the natural log of 25 divided by the natural log of 64 fifths. Okay? It's just a little bit easier to plug it into my calculator that way, but I do get the same answer. All right? If I look at the next one, we've got an investment that's earning an investment of $1,000, earning 8% APR compounded quarterly. We want to find the number of years needed for the investment to double. Okay, so a couple quick things here. It's being compounded quarterly. It's not continuous, so I know I'm going to use my standard model for growth, the y equals a times 1 plus r raised to the t. I know it's growth because I'm investing, which means I want to get more money out than I put in. The initial amount is the 1,000. Then I have 1 plus r, and this is where it becomes a little bit tricky. Keep in mind that this is 8% APR, but it's compounded quarterly. So this is a yearly rate compounded quarterly, so my units don't match here. If I want that 8% compounded quarterly, that's 8% per year, which means it's 2% per quarter. In other words, I have to take that 0.08 and divide it by 4. Because I want to change that to a quarterly percentage because it's being compounded quarterly. All right. Now the other effect that that has is that means that when I solve for t, my t is going to come out in quarters. So we've got to be super aware of these units. My rate is now in terms of quarters. My time is going to come out in quarters. And I want to know when my investment is going to double. So if I put $1,000 in, I want to know when I'm going to get $2,000 out. And now I'm just going to solve this for t. So I'm going to divide each side by the 1,000. Gives me a 2 equals. In here, this is going to be a 1 plus 0.02, which is just going to be a 1.02 when I simplify it. If it doesn't simplify nicely like that, we can just leave it as a big giant fraction in there. And now I'm going to take the natural log of each side. The natural log allows me to bring that exponent down, so I bring the t out front. So I have t natural log of 1.02. And now I have t times a value. I'm going to divide by that value, which is my logarithm. Now again, this is a job for my calculator, so I plug it in. And that gives me t equals 35.00 to 2 decimal places. But keep in mind, that's 35 quarters. And this asks me to give the answer in years, so I have to divide that by 4. All right. When I divide it by 4, I find out that my time, let me scoot this guy over, that my time ends up being 8.75 years. Okay, so be aware of your units so that you're giving the answer the way it's being asked. Okay. Number 16, it says a new car costs $22,350. It's depreciating at 20%. And really, this is per year. Should have been specified here, so 20% per year. We want to know how much will the car be worth in 10 years. So this is my depreciation. It's per year, so it's y equals a times 1 minus r raised to the t. And I just plug in what I know. I know that the initial amount was the $22,350. I know that the percentage decrease is the 0.20. And then I know that time is 10 years. Again, this just becomes a job for my calculator. Make sure that you follow order of operations when you do this, and you do the 1 minus the 0.2 first. You raise that to the 10th power, and then multiply by the 22,350. Okay. The most common mistake here is that we do the multiplication before we do anything else, and that gives me $2,399.81. Okay. And since it's money, we're automatically going around to 2 decimal places. And then I asked the question, when will the price of the car be $5,000? So this time I still have the same initial amount, and I still have the same percentage in here. But now I'm looking for time, and I want to know when this thing is going to equal the 5,000. All right. So now I'm going to divide each side by the 22,350. And you have a couple options here. You could try plunging this into the calculator, although it might give you a decimal that you don't want to round off. If you round off here, it's going to really affect your final answer. So what I'm going to do is I'm just going to leave this as a fraction. And you can reduce this fraction if you would like, but you don't have to. We're going to be plugging it into the calculator anyway. Over here I have a 0.8 raised to the t. And now I take the natural log of each side. And this is why I didn't bother reducing it. I'm just going to be punching that into a logarithm anyway. That allows me to bring the t out front, so I have the natural log of 5,000 over the 22,350. Here I can bring the t out front, so I have t times the natural log of 0.8, and now I divide by that logarithm. And once again, this is going to be a job for my calculator, so I plug it in. And when I do that, it gives me approximately 6.71 years. Okay?